Hey everyone, we're going to look at another geometry theorem, Euclidean geometry theorem, theorem 2, and this is how it goes. So it says the angle which an arc of a circle subtends at the center of a circle is twice the angle it subtends at the circumference of the circle. So angle at center is equals to 2 times angle at the circumference. Okay, so we're given a circle with center O. A, B, and C are all points on the circumference of the circle. So we are required to prove that AOB, this angle here, is 2 times ACB, which is this angle up here. So this is the angle at the center. That one is the angle at the circumference, and they're both subtended by the same arc AB. Okay. Proof. We construct or join CO and produce it to N. Then we label this angle here C1, this one C2, this one O1, and this one O2. Then we say that O1 is equals to C1 plus A. O1, this angle here, is equals to C1 plus A. That's the exterior angle of a triangle. But we see that C1 also is equals to A, because this OA and OC are radii, and this makes them angles opposite equal sides because they are equal sides. Similarly, if we also, when we substitute C where A is, we end up with this equation here, where O1 will be equals to 2 times C1. And similarly, if we go into this other triangle here, we will see that we can repeat the same procedure and get that O1 is equals to 2 times this angle here. Okay. Now we equate the two equations that we came up with, this equation and this equation. We add them, not equate them, but we add them. So the left-hand sides are added together and the right-hand sides are also added together to give us this. Then here we'll factor out a 2. Then we'll see that O1 plus O2 is the whole angle AOB, and C1 plus C2 is the whole angle ACB. So it means we have proved our theorem. Now, this diagram could have come a different way, and this is how it could have looked. And the same procedure would be followed, and the same everything would be true still, and we'll be proving it the same way. So here we'll have O1 and O2, and it would still be equal to a C1 plus A, and then these OA and OC are radii, which makes A and C1 equal as well. So the same procedure that we followed here also applies at this angle here. Then again, theorem 2 could have come this way, where angle C has gone this direction. So this is still angle AOB, and this is angle ACB. But now, how we choose our sides, or how we name O1 and O2, is a little bit different. So O1 will be the angle that is out here, the acute angle under here, but O2 will be the whole angle from line ON to OB. And then again here, this side, C1 will be this small angle here, the acute angle in here, and then C2 will be the whole angle from OC to BC. then the proof will follow like this. Same as before, statement, the given information. Then we joined CO and produced it to N just like before. Then we say O1 equals to C1 plus C2. This is C1 plus A, exterior angle of a triangle in triangle AOC. Again, we say C1 and A are equal. Substituted here where there's A, we get O1 equals to 2C1. Similarly, we do the same thing in the other triangle, OCB. Then we get that the whole of O2 will be 2 times C1, C2. Then this gives us this, but this time to get our angle AOB, we are not adding the two equations, we're subtracting the bigger angle with the smaller angle to be left with this AOB here. The same applies this side. We're subtracting the C2 from the C1, or the C1 from the C2, sorry. Then we factor out a 2 here. Then C2 minus C1 is our ACB, and O2 minus O1 is our AOB, which means we have proved the theorem. On GeoGebra, we see this diagram, the same diagram from the proof. Then we're able to verify that indeed angles that are in the center will always be double the angle at the circumference. So we can move around these points, and we see that this angle multiplied by 2 always gives us this. The numbers might not be exact in the decimals because of rounding, but you see that more or less if this angle changes here, this one changes accordingly, and it's always half of this red one. So I can even get it to be an exact integer, which is proving to be a little bit difficult. Okay, but you see the gist of it. And then if you move this other point, nothing changes. It doesn't matter where that C is, it remains the same value as long as this one does not change. But as soon as we change this one, it changes as well. So this is how that first diagram looked. Okay, and then this is how diagram C in the proof looked. So this angle is 2 times this angle. And then this is how diagram B, the second part of the proof that I did, looked. This is how it would look like. And then you see this is 46.3 multiplied by 2 gives us 92.6. So yeah. You can play with this the whole day. So like and subscribe, share the videos, and I'll see you in the next one.